All right, so everybody needs to make sure that they have a nice clean periodic table and some colored pencils. Everything's over on the side counter. And we're going to mark up your periodic table, the one that you're going to keep all year long. You can write a bunch of stuff on it, equations, as we go through the rest of the year. You can put a lot of information on it, and you can always use them for tests and quizzes. So make sure that you have a nice clean periodic table you haven't written a bunch of stuff on yet, and some colored pencils, and we'll get started. All right, so first of all, we're going to talk about the periodic table by talking about a grocery store. I think everybody here has been to a grocery store. And the periodic table, believe it or not, is like a grocery store. It's set up the same way. Okay, so when food is delivered to your grocery store to be put on shelves for you to buy, they don't just put everything that comes off the truck on the first shelf that they come to. The grocery store is organized. They have all these different sections. They have a snack aisle with cookies and potato chips and crackers and things like that. They have a candy aisle. They have a frozen foods section. They have a dairy section. And so here, just to emphasize this point, I have a grocery list off to the right: potatoes, milk, canned pumpkin, flour, all that kind of stuff. And we're going to place these on the aisle that they belong. So we're going to see where each of these little individual things belong in the grocery store. And we'll start with canned pumpkin. This is the season. People make pumpkin pies and things. You buy pumpkin in a can, and you find that on the baking aisle. And then you need some flour. Well, that's also on the baking aisle. Some sugar, some vanilla, ginger, nutmeg, cinnamon. All those are on the same aisle because they're all similar. They all do or are used for basically the same thing: baking and cooking. They're ingredients of making baked things. If you're looking for sweetened condensed milk, that's also there because that's used in making pies and candies and things. If you need garlic powder, it's also with the spices on the same aisle because they're these basic dry ingredients, canned ingredients for making things. If you need marshmallows, they're generally there. People eat marshmallows, but they're also used for baking and making things. So all of those things, even though they're seemingly pretty different things, they all have the same use. So they're all put on the same aisle. So they're easy for everybody to find. And this is the same in grocery stores all over the world. It doesn't matter where you go, they're going to have aisles for all this baking stuff. All right, and then if you look for milk, well, milk isn't on the baking aisle. You use it for baking, but it's over in the refrigerated dairy section, along with eggs, butter, and whipped cream. They're all similar. They have to be stored similarly. So they put them in the same area. And then since it's always the same, no matter where you go in the world, if you run into the store for a few things, you know where to go. You know the aisle you need to be at. If you're looking for bread, everybody knows that's in the bakery aisle. It's not something that you use to make bread like in the baking aisle. It's already made. It's going to be in the bakery. If you need some potatoes and some onions, those are with produce, with all the other fresh fruit. All right? And so if you can remember that the grocery store is organized in these aisles, in these columns, it makes understand the periodic table a little bit better, a little bit easier. So here, this is the periodic table as it appears, our chemical grocery store. And this isn't how you're used to seeing the periodic table, but this is the way the periodic table actually is. But if you notice, it's really long and thin. It doesn't fit on a piece of paper very well. So what they do is they take these two rows here, from number 57 lanthanum over to 70 ytterbium, and from 89 actinium over to 102 nobelium. They take those two rows and they take them out of the periodic table and then squeeze it together so that it all fits on a piece of paper. So the periodic table, that's the way it's set up and designed. But in order for it to fit on a piece of paper, a standard piece of paper, They take that row, those 2 rows out of the bottom, and it all fits. All right, so you have your periodic table, and we're going to start to mark this up, and there's a few things I want you to notice. I want you to notice here, in this is called Group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, and France. They all have a charge of +1 normally. Most atoms are neutral, but all of these ones in this first group have a +1 charge because they like to lose the 1 electron that they have. All of these have 1 outer valence electron, and they like to lose that negative electron, giving them a positive charge. Okay, so this is like one aisle in the grocery store. All of these elements act similarly. Okay, if you go to the second one, it's a +2 charge. This group has 2 valence electrons, 2 outer shell electrons that these atoms like to lose. So they lose 2 negative charged electrons, they become +2. And all of these in this group are similar. They act the same way. If you notice, there's calcium in there, number 20, and you know that your bones have a lot of calcium in them. Well, if you don't have a lot of calcium, your body will replace it with magnesium or beryllium or strontium or whatever it has with a +2 charge, a metal with a +2 charge. They're all similar. We go across to above boron there, it's +3. That's because these elements have 3 outer valence electrons and like to lose 3 negative electrons to become +3. You go over one more, it's plus or -4. These elements have a +4- charge because they have 4 valence electrons. All these atoms want to get to 8. They'd like to have 8 valence electrons. I'm sure you heard that in 6th or 7th grade science. And these ones, since they have right in the middle, they can either lose 4 electrons to become +4 or gain 4 electrons to become -4. We have -3. These ones have 5 valence electrons, and they like to gain 3 negative electrons to become -3. This group is -6, or it has 6 electrons, so it likes to gain 2 negative electrons to become a -2 charge. This group right here is these are the halogens. They have 7 valence electrons. They like to gain 1 to have 8. That means they'll have a negative charge, -1. And then we get out here where these elements have no charge. These are the noble gases. And they have 8 valence electrons. They're happy. They don't like to gain or lose. They're happy where they are. So they're happy being neutral. All right. So here, let's mark up a few things for your periodic grocery store of the elements. So here, the periodic table is read left to right, top to bottom, just like a book. Up in the upper left-hand corner is hydrogen. Hydrogen is hydrogen because it has 1 proton. That's what makes it hydrogen. 97% of the universe is hydrogen, just protons floating around. Left to right, you go over here to helium, 2 protons. It's helium because it has 2 protons. Then we go to 3, left to right, top to bottom. Lithium. It's lithium because it has 3 protons. It's beryllium because it has 4 protons. It's boron because it has 5. It's carbon because it has 6. And it just continues like that, left to right, top to bottom, all the way down. You just keep counting, adding protons. There's just a little bit of it's not a glitch here, but it's because they take those 2 rows out of the bottom of the periodic table and squeeze it together. You notice cesium here is 55, barium is 56. Well, then you'll notice that right next to it is number 71. Well, that's not 55, 56, 71 isn't right. But remember, these 2 rows belong right in here. So 55, 56, 57, 58, 59, 60, 61, all the way over to 70 at terbium. And then after 70 is 71 lutetium, and then it just continues on to 72, 73. Left to right, top to bottom, all the way across. Then you go down to the next row. Okay. Now, I don't want you to color in. I'm going to color a couple of sections here, but I don't want you to color these in. I want you to label this part of the periodic table and another part of the periodic table, but don't do any coloring in right now. We're going to start, I think yours already has the staircase there where it's kind of darkened and highlighted. This is the staircase on the periodic table that divides the elements into their different sections, into two main sections. Okay, those on the left of the staircase are the metals, and please don't color this in like I did. I'm just trying to show you. These are all metals, except you notice hydrogen over here is not a metal. Hydrogen can actually be drawn all the way over here next to helium. It's not a metal. And metals are good conductors of heat and electricity. That's how they're defined. They are soft. You don't think of things like iron and calcium in your bones being soft, but pure metals are soft. You can cut them with a butter knife. They are ductile, which means they can be pulled into a wire, and they're malleable, so they can be pounded into sheets like aluminum foil or tin foil, or how they make aluminum cans. All metals are soft, and they conduct heat and electricity. That's to the left of the staircase. To the right of the staircase is the nonmetals, and those don't conduct heat and electricity. So metals conduct heat and electricity. Nonmetals do not conduct heat and electricity. And it seems kind of odd. We think of metals as hard and brittle, but they're not. Metals are actually soft when they're pure. It's these nonmetals, when they are in the solid form, that are rock hard. Carbon, if you think about it, charcoal, diamonds are the hardest substance in the world, and they're made out of carbon. It's the nonmetals in the solid form that are hard. Frozen nitrogen, oxygen, fluorine, they're all just solid. Even when they're mixed, silicon dioxide or sand it's quartz, it's hard. H2O, water, when you freeze it into ice, it's very hard. If you've ever fallen on the ice, you understand that ice is very hard. Okay, and then these shaded ones right in the middle are called metalloids. So metals conduct heat and electricity. Nonmetals do not conduct heat and electricity. Metalloids kind of conduct heat and electricity. And these are ones just above and below the staircase. And you've probably heard of these elements in relation to computers and chips that control computers. Boron, silicon, germanium, arsenic, antimony, those are the things computer chips are made out of. You don't want to make computer chips out of pure metals because they just don't let electrons flow freely. You don't want to make them out of nonmetals because electrons don't flow. They don't conduct electricity. You want a metalloid, which kind of lets electricity pass through. And all computer chips do and computers do is count electrons. They're a binary language, ones and zeros. That means 1 means an electron flows through the chip, 0 means it does not. And so all computers basically do is count electrons. So you need to be able to have something that lets a little bit of electricity flow. That's why they don't make computer chips out of silicon or out of metals, because that's all the electrons flowing through freely. You don't make them out of nonmetals because it doesn't make any electricity flow. You use metalloids because they let a little bit of electricity flow. All right. And now you can color up your periodic table here. This first group, starting on the left, is the alkali metals. Now I know I've colored in hydrogen here. That's because it's a +1. It's not a metal. It's not an alkali metal, but it is a +1, the same as all the alkali metals. Lithium, sodium, potassium, rubidium. And they are chemically similar. That's why they're all in that first column there, because they're chemically similar. They're in the same aisle of the grocery store. And those are called alkali metals. They have one valence electron shell, electron. The second group is called the alkaline earth metals. They have 2 valence shell electrons, which they like to lose and become a +2. This is our next column, our next aisle in our grocery store. They all act similarly chemically. Right here in the middle, this big chunk in the middle, are called the transition metals. They all technically have 2 valence shell electrons, although they form different charges. If you notice there's no charge above this group, that's because they form various charges, like iron can be +2, +3, +4. Nickel can be +2, +4, +6. A lot of these elements will form multiple charges. There's only a couple that don't. And as far as transition metals, they go right up to underneath the staircase, and it includes these metalloids, germanium, antimony, and polonium. All right. And then schnapps. Those are the chemicals of life. I don't want you to color these in. I just want you to sort of bracket them, draw a circle around them, or color in the border around them. These are what 97% of you and every other living creature on this planet are made of. You're made of hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. And it's called schnapps. So you notice I didn't color them in, I just sort of highlighted them. These are the elements of life. You obviously have about a lot of calcium in you, but you're about 1% calcium. So it's not included in there. But your life depends on carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All right. We'll move on to the carbon group, well named. It's carbon and silicon, and this is the basis of life. There's 4 valence electrons, and carbon can make 4 bonds. This is how, if you've taken biology or organic chemistry or something, this is what makes carbon special, because it can form 4 bonds. It can make these long chains, amino acids and proteins and DNA and all this, because it has 4 different spots to bond. Silicon also has 4 different spots to bond, but for various reasons it's not ideal for life. But that's the carbon group, 4 valence electrons. You go over to the nitrogen group, that's 5 valence electrons, like to form a -3 charge. And again, it goes down to the staircase, nitrogen, phosphorus, and arsenic. The next group, I know it should be called the oxygen group, but it's not. It's the chalcogen group. 6 valence electrons, likes to form a -2 charge. Oxygen, sulfur, selenium, and tellurium, all the way down to the staircase, not going below it. And these are all the oxidizers, which means they like to take electrons from other atoms. Their oxygen is oxidizing is named after oxygen, because oxygen is a powerful oxidizer, and obviously you need it to live. The next group is called the halogens. These have 7 valence electrons, like to form a -1 charge by taking an electron from another atom to get those 8. Fluorine, chlorine, bromine, iodine, and astatine. And you'll notice that this has a lot of those diatomics, F2, Cl2, Br2, I2. That's because fluorine, chlorine, bromine, and iodine, along with oxygen, nitrogen, and hydrogen, do not exist in the universe by themselves. If you see the word fluorine, it means that there are 2 fluorine atoms bound together. Okay, we get to, and the same with chlorine, bromine, iodine, oxygen, nitrogen, and hydrogen. Go to this last group that has 8 valence electrons, so it's got a full outer shell. These are called the noble gases. You probably know that. Helium, neon, argon. They're unreactive. They don't like to do anything because they have those 8 valence electrons. They don't like to give any up, and they don't like to gain any electrons. They're happy where they are. Those are the noble gases. So make sure you get it doesn't matter that you use the colors I used. You can use whatever colors you want. But make sure you differentiate the alkali, the alkaline earth, the carbons, nitrogen, chalcogens, all that. We go down to those bottom 2 rows, and they're aptly named. If you notice, number 57 down here is called lanthanum, and this whole row here are called the lanthanides. So you can color those in one color, whatever you want, named after lanthanum. And these are what are called the rare earth metals. They're not really that rare. They're in the Earth's crust. They're naturally occurring, and a lot of those are also used for modern electronics. And the vast majority of them are mined in China. China controls like 95% of the rare earth metal market, and those are necessary for modern electronics. This last row, number 89 here, is actinium, and this group is called the actinides. And here, so it's 89 for actinium, 90 for thorium, 91 for protactinium, 92 for uranium. Uranium is the largest naturally occurring element. That means anywhere in the universe you can find uranium. It's produced like everything else in star explosions and planet formations. Anything after uranium is not natural. It's man-made. Here, this is uranium. In World War II and just before World War II, as they were doing nuclear research, they created neptunium in a lab, and then plutonium, and then americium. And a lot of these here, 93 all the way out to, I think, 103 or 104, were created at one lab at the University of Berkeley in California by Mr. Seaborg and his group, and they named them after California, America, Berkeley, California, Einstein, Fermium, Mendeleev, the creator of the periodic table was Mendeleev, the Nobel from the Nobel Prize, Lawrence, Rutherford, great British scientists who worked on the atom over a century ago. And then you get to 105 dubnium. This is the first one developed by Russia. And then Seaborgium, named after Seaborg, the guy who identified and created all of these and named all of these first 10 or so man-made ones. And then the rest of them are developed by Russia, Germany, and Japan. You get all the way out here to 118, which is now named, and it's named on your periodic table. I think it's Augustin, and that's named after a Japanese lab that developed it. But so the first 10 or so man-made ones were American, and the rest were Russian, German, Japanese, but named after people or places where they were developed. That's it. Color up that periodic table and make sure you keep your periodic table.